Hello all. We're going to be studying the effect of temperature versus pressure today, and we'll also cover temperature versus volume. There is a project associated with this lesson. It's basically a cartoon book, and you can read my description here, but I can explain it better in class. So just make sure that you ask me to go over the details of the project. This date is from last year, so we'll discuss a due date together. And what you need to write down actually as the first thing in your classwork page for this notes is this aim. What are the relationships between temperature and pressure and between temperature and volume? And add this aim to your essential questions handout, but additionally, I want you to have it at the top of your classwork page. And then follow it up with these do now questions, which we will answer in class. Please do not answer them before class. All right, so temperature. The definition of temperature, as you may remember, is a measure of the average kinetic energy of a substance, which brings up an important point. What is kinetic energy? So it's the energy of motion, and it can also be described with this equation. It says that kinetic energy is 1/2 the product of mass times the velocity squared. If you wanted to increase the kinetic energy of a particle, you could do two things. You could increase the particle's mass, or you could increase the particle's velocity. However, changing the mass of a particle is actually not feasible in chemistry because these particles are so tiny. Therefore, if you want to increase the kinetic energy of a particle, which we also know is similar to temperature, you must increase its speed or velocity. That's why I have a speed racer up here. Okay, so if I increase the temperature of the gas inside a container, the particles will speed up. So maybe at one temperature, like a lower temperature, the particles will be colliding with the walls of the container at a specific rate. But if you increase the temperature, they'll collide more frequently and more often. Therefore, if you increase the speed of the particles inside a container, the number of collisions would also increase. And if the number of collisions increases, the other thing that has to increase is pressure. So that means that we have, between temperature and pressure, we have a direct relationship. And I say that because if you increase the temperature, you increase collisions. And if you increase collisions, you increase pressure. Therefore, the graph of temperature versus pressure would have to be a straight line with a positive slope. So something like that. Or it doesn't have to be a 1-to-1 slope. It could be a lower slope, but it's going to have to be direct, and which would be a straight line. Okay, you can also relate temperature and volume. So if I increase the temperature of the gas inside a container, the particles will speed up. And if the speed of the particles inside a container increases, then the number of collisions must also increase. And this is the trick on this slide as opposed to the previous slide. In this slide, we're going to see an animation of an apparatus that has this movable ceiling roof over the gas chamber. So basically, as the particles speed up and have more collisions, which increases the pressure, then they're going to move the ceiling up. All those collisions will make the ceiling move up in the air, which also is increasing the volume of the container. So basically, the particles speed up, which is going to increase collisions, which is going to increase pressure, right? Which we just said. And in the previous lesson, right before this one, we talked about pressure differences on two sides of the walls of a container. And we determined that if the pressure inside a container is greater than the pressure outside the container, that the container would either explode or implode. But if the walls are flexible, then it wouldn't explode or implode. If the walls are flexible, the container's size will just change. It'll expand or contract based on pressure differences. So if the pressure inside is larger, the wall will expand outwards, which is like a controlled version of explosion. So I said that the volume of the container will increase. So this also reveals the relationship between temperature and volume. Assuming that the walls of the container are flexible, it's a direct relationship, meaning that if you increase the temperature of a gas, the volume will also increase. So the shape of the graph will be the same shape as the previous slide. It's going to be a straight line positive slope. It doesn't have to be steep, it can be shallow as well, but it has to show direct relationship by when one increases, the other increases. So this is like a long chain of cause and effect. So this slide is going to sort of help us put it all together. So let's say that you're heating a substance. That means the temperature is increasing. And increasing the temperature is the same thing as saying that you're increasing the kinetic energy. Kinetic energy is, I'll put the equation here, 1/2 mv squared. So if you're increasing kinetic energy, you're also increasing the velocity. And increasing the velocity will increase the frequency of collisions. If the walls of the container are rigid, meaning they cannot flex, then increasing collisions is going to increase pressure. But if the walls of the container are flexible, then increasing collisions will increase volume. If you cool a substance, of course, the temperature is decreasing, and that means that the velocity will decrease as well, according to the same equation. Ke is 1/2 mv squared. So velocity will decrease, and decreasing the velocity decreases the collisions. Now, if the walls of the container are rigid, decreasing the collisions will decrease the pressure. But if the walls of the container are flexible, decreasing collisions will decrease the volume. And we finally reached the pair-up. So I want you to copy down all this information here, but especially these numbers. There's a formatting issue here. It's really is going to say 6.02 by 10 to the 23rd, not to the 1023. It's also, you can think of it as being this number, which is a huge number. And it's very similar to the idea of a dozen. It's just that a dozen means 12, and this is a mole, this guy right here. And a mole means this number. So it's a very large number because we use it to describe molecules, which themselves are very small. So we need a unit which is much larger. And I'm only bringing it up because it's mentioned in these two questions down here. So I just wanted you to know that it's just a number. It won't affect our answers, which we'll do these in class, but yeah, I just wanted to mention it. So copy down these pair-up questions underneath your aim and your do now. And our summary is going to be this guy right here. So it's going to be a little demonstration you'll see in class. So you'll need to copy down this Regents question to get started, and then we'll copy down this table as well, and we'll fill in the data in class tomorrow. So I guess the last thing here is this question, which we'll answer in class tomorrow as well. Thanks for watching.